Okay, so this one is a satellite, instead of being, what was the last one, like 600 or something like that? Yes, 5,200 kilometers. This one is just going to be 300 kilometers. So just kind of get in the habit of doing this. Let's just rewrite this as 300 times 10 to the third, otherwise known as 3 times 10 to the fifth. Now I'm still not friendly with my calculator, so I'm going to move the decimal place over one more place, because I remember that the radius for the Earth is in terms of 10 to the sixth. So if I have them both as the same exponent, it becomes easier just to add these values together. So then I get this distance, moving it over one more place, is 0.3 times 10 to the sixth meters. Now I'm doing this, I'm doing something in terms of the velocity, its tangential velocity in its orbit, the period of the orbit, and center-seeking acceleration. But to get to any of these, I need to remind myself that the thing that I was looking for is that we said what? We said that V, and if you don't know where this came from, you need to watch the previous video, equals the square root of GM over R. So I need R. So I need to add in the radius of the Earth, which is, I should have memorized by now, but I still don't. So I'm going to look it up. It is 5.2 times 10 to the sixth. That is not right. That was the last one. 6.3 times 10 to the sixth meters. And so now I see this is easy. I can just add these straight away. So my R value here is just going to be 6.6 times 10 to the sixth meters. And then don't forget, I said, let's just go ahead and calculate out GM. So the product of GM is 3.988, 7 times 10 to the 14th. And if you're not sure where that came from, you want to take a look at the previous video, but just to quickly remind you, this is the gravitational constant, and this is the mass of the planet being orbited. So in this case, this was the mass of Earth. So now I can go straight to the velocity of this satellite. So I get the velocity of the satellite is the square root of 3.9887 times 10 to the 14th divided by R, which is this thing that we calculated here, 6.6 times 10 to the sixth. And if you want, you can do the same thing. We can subtract 6 from 14. So that would give us like a 10 to the 8th up top. And then it just becomes 3.9887, 10 to the 8th divided by 6.6. It's just eliminating errors as far as your calculator use goes. So I put that in there, and what do I get? I get that V, so that answers the first question. V is 7,727 meters per second. So let's see what happened here. For my last one, we were 5,200 kilometers. This is only 300. So this is considerably further. And when I look at what's happening here, I'm dividing this GM by this radius. So my velocity here was only 5868. So what's happening? If I'm in a stable orbit, then dividing by R, I expect this value to be larger, and indeed it is. So that's another way that I can double check to make sure that I haven't made any mistakes in calculating it. So let's see. Now we did center seeking motion and frequency and period. And if you remember, I drew a circle and I said, so velocity is 2 pi RF, and it also equals 2 pi R over period. And if you're ever trying to remember that, period is in terms of seconds. So I'm just going to remind you of that period has units in seconds, and frequency has units in seconds to the -1, or 1 over seconds. So as far as velocity goes, well, let's see what we have here. That is going to give us a distance. That's the distance, the circumference of a circle. So that's the path covered going tangentially around a circle, times the frequency, the cycles per second that it takes to go around the circle. So this gives me meters over seconds, or meters per second. Period is in terms of seconds. That's the amount of cycles completed in 1 second. So this thing here is the same thing. So this is just my circumference, the distance around that circular path I'm taking, divided by the amount of time it takes to complete that. So they both give me the exact same thing. But I look over here, I have velocity, and I want to get to period. So let's see, I can go straight from here. I can go that V equals 2 pi r over period, or then period equals 2 pi r over velocity. So I have velocity, I'm determined what the radius is, so I can write this straight away as then the period equals 2 pi times this radius, 6.6 times 10 to the 6th meters, divided by the velocity that I determined here, 27 meters per second. What do I get a period of? I get a period of 54.31 seconds. So its period of rotation is 5,431 seconds. That's how long it takes it to make 1 lap around the Earth. Another way of thinking of this is you can do the conversion, and that is in 1.5 hours, it makes a complete rotation around the Earth. So those satellites, that should kind of make sense. If you've ever laid outside and looked up at the stars, and then you see something that is high up above, so it's not a plane, but it's definitely up there, and then you track it with your eyes, and you can see it steadily moving across the sky. And it doesn't take that long for it to get out of your field of view. That's because those things are moving fast. I mean, that's a low satellite, but even if I did the same thing for my one that was more realistically 5,200 kilometers above the Earth, I'd find out that it's making a relatively fast time making its complete orbit around the Earth. So that's pretty cool. So now what about a center? So this is my center-seeking acceleration. Or another way to think about it is this gets me to G, because I can use the center, I can use AC equals V squared over R. Or another way to look at this is GM over R squared. How did I get to that? Well, let's think about this. I have my force of gravity equals my mv squared over r. This thing here is my A. So I want to solve for this, and I know that this piece, when I write it out, is that GM little mass over r squared. So my masses are still going to cancel. Little masses still cancel. And I'm left with my G is this value. This would be my acceleration due to gravity if I'm on the Earth. So my acceleration, center-seeking acceleration here would just be the GM over r squared. And I can do all of that work back here, and I look at this, I'm like, So here's V squared. So if I square things up, bada bing, bada boom, I end up with this expression. Sorry about that. Okay. So I end up with this expression. Why am I not canceling these out? Well, the reason for that is this is my center-seeking acceleration, right? So if I want A, I don't want to isolate and cancel out those R's. So my center-seeking acceleration is going to be in terms of GM over r squared. They won't cancel. They would cancel if I was solving for V like they did up above here. So when I put everything in, I end up getting that A. Oh, did I solve for that? I didn't. Oh, so sad. So I get that my A center, I swear I did. A center equals GM over R. Well, we wrote out the GM is 3.9887 times 10 to the 14th divided by R squared, 6.6 times 10 to the 6th meters. And that quantity is squared, and let's see what we get. And I get that A is 9.16 meters per second squared. So compare that to G. That's one of the things that Mastering Physics loves to do, is what is this ratio between this acceleration and G on the surface of the Earth, where G on the surface of the Earth is 9.8 meters per second squared. So that tells me this satellite is way too low to even be considering this for that, because this should be a lot smaller than it was. Now the other shortcut I could have done is just jump right here. If I want this, I can put in the B that I solved for here and divide by R. I get exactly the same answer that I did. So both are fine. This is a bit of the longer cut, just kind of giving you where those parts and pieces came from. But once I've already solved for velocity, I can definitely just jump right to here. Now, a note of caution, don't freak yourself out, because there's rounding here and there's some rounding here. So depending on how many values I put in, I can get anywhere between 8.94 and 9.16, what can make you talk yourself into thinking that you're doing it the wrong way or that they're not the same, but it's all a result of rounding. So let's move on to R next.